This is a one sample t-test and confidence interval example. It's example 2 from class examples. It's about batteries. So I'm going to assume that you have read the problem and understand that what we're trying to do is we're trying to prove the alternative hypotheses, and that is that HA is that mu is greater than 30 or 300. We want to say something to the effect that the batteries have a mean lifespan of over 300 minutes. So the company has met its goals. All right, so the null hypothesis is that mu, the population mean, is 300. So the batteries have a mean lifespan of 300 minutes. And then we would say something like the company has not met its goals. All right, so this is what we want to prove, is the alternative. So we want to see that the null hypothesis leads to a contradiction. So one of the first things you need to do is get the data into a list. Okay, so I've used L1. All right, before we go too much further though, let's check the conditions. So the random condition So here they did not say it was a random sample of batteries. So what we're going to say something is that the 12 batteries produced for this test should be representative of all the batteries produced. Okay, so we're assuming that there's a consistent manufacturing process. So it's an assumption, okay, and then the 10% condition, certainly 12 batteries is less than all the batteries produced. Less than 10% of all the batteries produced. Okay, so I'm scribbling because I want to go fast. I want to get to the nearly normal condition. Okay, that's the new thing. Okay, so just following along on my calculator, what I did is I went to stats, I think it's stats, calculate, something like that, and you get one variable stats. I use one variable stats, And here I can see here's my mean for the sample, and here's my sample standard deviation, and of course the sample size is 12. Okay, so x bar, I really can reuse this, but this is x bar, s, and n. Okay, so then what I do is I go to stat plot, and I select plot 1, make sure the others are turned off. I select histogram, put in L1, and make sure the frequency is 1. Also go to, if your button y equals, go check that and make sure that there's no equations in there. Okay, and then from that I did zoom, hit the zoom button and do zoom 9 and enter, and this is what I get. I get this histogram, and this would be fine. You don't have to really, you can use this. Here's the window. If you hit the window button, you can see what zoom 9, what it did is it automatically created these conditions. So this is the x minimum value and the x maximum value. So if you wanted to draw this, hit trace, and you can see that there's 2 here, 2 here. This must be 3, 2, 2, and 1. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, now I was not completely happy with that, although it is unimodal and pretty much symmetric. It's just not very interesting. So what I did is I went into the windows and changed the parameters just a little bit. I started at 240, so you can see I knew kind of where I was at. I started at 240 and went to 380 and then changed the increment to be 20. I increased Y size so I could see everything because it got chopped off the first time. Okay, so now I get 1, 1, 3, 2. Still should have 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so it doesn't really matter, but sometimes you can clean up the histogram and make it look a little bit better. So the bottom line here is that the distribution, I want to say something like this, the distribution of battery lifespans is roughly unimodal and symmetric. So it is reasonable, let's say, to assume that the lifespan of all batteries could be described as or by a normal model So what we're basically saying is going back and saying, well, so this sort of suggests, there's nothing to suggest that the population is not normal. So not normal. Okay, and if the population is normal, then we know that the sampling distribution is normal. Okay, so that's sufficient, a sufficient check for the condition. So we're going to say since the conditions are met, we will proceed with a one sample t-test using a student's t-model with n minus 1, so 12 minus 1, 11 degrees of freedom. Alright, so now let's not mess around too much. So we have this model, something like that. The center we hypothesized was 300. Okay, the center was 300. So what's the standard deviation? Well, the standard, we'll have to approximate that with the standard error of x bar. So let's see, that's going to be this, we'll take the standard deviation of the sample and divide it by the square root of n. So the sample standard deviation, where was that? It was right here, 29.311. So 29.31 divided by the square root of 12. Okay, and I get 8.461. Okay, so if that's the case, then I can quickly calculate my t value. So t, and I'm going to use just the subscript here of 11. So that's going to be x bar minus mu divided by the standard error of x bar. Okay, so then that's 8.4. Wait, my bad. Slow down. I was going too fast. 8.461 is down here. The hypothesized value is 300, but we kind of skipped over our observed value, right? This is the observed value, or observed mean, 306.25. So 306.25. Okay, and so that comes out to be 0.7387. Okay, so now if we can kind of sketch in where our, this is pretty sloppy, but I'm trying to go fast. So if that's one standard deviation away, this is going to be right about there. So we're going to have a big p-value, aren't we? You can tell already. So the p-value. So what we need to do there is we have to use t-CDF. So if you do second distribute, right, DISTR, you get this menu, and so you say the p-value, that's equal to the probability that x bar is greater than 306.25, which is equivalent to saying the probability of t is greater than 0.7387, and that can be computed using t-CDF. And we want to go from here, 306.25 or 0.7387. So 0.7387 out to infinity, and then what's different is we have to put in the degrees of freedom, which is 11. All right, and that gives me a p-value of 0.238. Okay, so somebody might have said, hey, how come I didn't specify an alpha level? Well, I didn't know. Probably it would be a good idea. All right, but with a 23.8%, that's just so big. okay, that we're going to say the p-value is high, so we fail to reject HA. Okay, there is no evidence to suggest that the mean battery, God, that was pretty bad, huh? The mean battery lifespan exceeds 300 minutes. So we could say, therefore, executives aren't going to want to hear this. Therefore, it does not appear that the company has met its goal. Okay, so don't be the one that has to stand up in front of the executives to say this. Get somebody else to do it. Get a young employee to do it that doesn't know better. This is a politically incorrect thing to say. This means that people aren't going to get their bonuses. But as a statistician, we just do our jobs. Okay, so anyway, there you go. That's part one. I'm going to come back and do a video on how to do the confidence interval. So I hope this helps.